recording and session. So this session is one of my favorites because we start to have enough foundational material that we can go through some examples in literature. So this is an example. I won't go through this one in depth because this requires some material from next week, but it gives you a sense of how hype this is. So this was published last year and it caught the eyes of a lot of physicians. A lot of physician Facebook groups were posting about this paper, and I really want to jump in and say something, but then, not a physician. So they developed a neural network that they say can detect COVID with high accuracy. By high accuracy, they mean an AUC of 0.97, which is incredible. That's better than pathology in some cases. They can detect COVID just by recording the sound of your cough. And they reported these accuracies. So people are thinking, hey, this is legitimate. Maybe we can deploy these in low resource areas or something. But then as you read this paper, so I'll send this paper to everyone afterwards. This is just a teaser. There are some things that they didn't do so well in terms of their data splitting. So even just looking at table 1, before we look at their actual method, we see that if you look at the distribution of symptoms, the negative patients without COVID, not many of them had a cough at all, right? Only 9.8% had a cough, and less than 2% had difficulty breathing. So if you just diagnose based off someone having a cough, it means you're having COVID, you'll have a 91% accuracy with their data set. So remember last week we talked about proper best practices in data splitting and data balancing. This paper doesn't look like they follow that. Like their method, it doesn't disprove their method. Their method might work, but it's not properly validated. So another method, so this was really popular. So this came out 3 years ago. This company called Cardiogram said they developed an artificial intelligence model that can detect diabetes from your Apple Watch with 85% accuracy. Wow. Right. So, I mean, everyone was really excited because this is an implication. So people who didn't know they have diabetes, now they can get earlier treatment and they can get screened earlier. So this would have been revolutionary if it was true. But as with many things in machine learning, this is a bit overhyped. So even to today, there's no FDA approved Apple Watch diabetes diagnostic tool. So going to the actual website. So this is their actual website, right? This is their publication on how they did it. So if you open the publication, first of all, it's a conference paper. It wasn't a full-fledged journal paper, which is sometimes that means that they didn't do their full due diligence because a lot of people just present ideas as a proof of concept. Or no, not this one. Yeah, this one. So this is their paper. So I'm not going to read through every part of it. I'm just going to go for the pertinent parts. So they have 57,000 person weeks of data. That's a kind of weird metric, but whatever. They had high accuracy for detecting diabetes, high cholesterol, hypertension, and sleep apnea. Okay, so the first thing I look at is how did they validate it? What is their data set and how did they validate it? So they had 14,000 participants, which is a great amount of patients. Anything above 10,000, that's usually what you see in Nature papers. But then, so the key word I was looking for was cross-validation, which does not exist in here. So that is already sort of a red flag. So, okay, fine, I'll look at for validation. So they did not cross-validate. Remember last week we talked about how you split your data set into test and training, and then you shuffle around what's the test data set so that you essentially run 5 trials of your testing. So they did something called hold-up testing, which is they had a subset of data for training, a subset of data for tuning their algorithm, and then subset for testing. So it's not completely externally validated. And you also need to validate it across multiple centers. So a lot of this, if you just screen their validation process, you can tell that it's not ready for clinical deployment. Okay, so that's enough of that for now. We'll have some more motivating examples later. So this week's really focused on these machine learning models and buzzwords you hear a lot in literature. Before I start, I have to acknowledge we're funded by UBC, Biomedical Imaging Artificial Intelligence, the Data Science Health and Research Cluster, Queen's Diagnostic Radiology, the AIM Student Society, and Queens is situated on the territory of Haudenosaunee and Anishinaabe, and UBC is situated on the traditional, ancestral, and unceded territory of the Musqueam people. So this is just recapping some really important concepts that I'm going to mention again. So in session 1, we define artificial intelligence as any sort of system that can sense its environment and complete some tasks. Machine learning is a specific way of doing that, where the system will learn from its mistakes. And then deep learning is a type of machine learning where you have a lot of intermediate calculations in order to perform that. Deep learning is more of a buzzword, just saying your machine learning model is really complex. So Michelle talked about the machine learning pipeline, where first you take some input variables, you create a model, and then you use that model to perform a prediction. And then you compare those predictions with some sort of outcome data that you have, some sort of actual outcome. And then you look at the error and then you update the model. Once that model is fully trained, then you can take it onto a USB, take it to some new patient data, and then you can now create a prediction with those new patients. So this is essentially how machine learning works. It's how that heart detect, Apple Watch heart diabetes detection thing work. They trained it on some other data, and then they brought it onto the Apple Watches. Now, today's agenda is specifically on specific machine learning concepts, mainly when to use artificial intelligence and machine learning, differences between supervised, unsupervised learning, simple models such as linear and logistic regression. So logistic regression is used commonly in biostatistics as a to get significance tests and odds ratios, but you can use it for predictive analysis as well. We'll go over decision trees, which is the most intuitive machine learning model for medical students. And then we'll talk about specific details of the training process, such as preparation, validation, evaluation, performance, and how to select the model. So again, machine learning is going to be an algorithm that identifies some sort of pattern to create a model to predict new data. So you only do it when there's a pattern or a signal. So the difference between supervised and unsupervised learning. So supervised learning is when you know there is an outcome. So I'm going to try to annotate here. Let's see if this works. So you have these blue dots and red dots. They're different classes. Say they represent people with and without heart failure, right? And then you have those outcomes. So when you train your model, you can compare your model's accuracy to the actual outcomes to update your model. Unsupervised learning is when you don't have those labels, but you do know your data is sort of spread out. So for instance, if you're looking at, let's say this is the patient's, I'm picking a really random variable like hair color, and they're segregated like this, then you can use some math to draw out the boundaries of these variables to create these subgroups. And hopefully these subgroups are related to some outcome. Most of the work that you'll be encountering in clinical practice will be supervised learning, because you're trying to usually predict some diagnostic outcome or improve some sort of workflow metric that you can measure, that you have existing evidence for. So semi-supervised is something like in between. Like you won't really encounter this. Okay, progress the slide. Okay. All right. Clear these annotation. Sorry, just trying to progress the slide. One moment. Okay, I'm just going to reshare the screen. Okay, so there are two different types of supervised learning. One is classification. That is when there is usually one or two outcomes, and you want to predict that those variables to be associated with that class. So whether patient has heart failure or doesn't have heart failure. Regression is when you're comparing to some sort of continuous variables, like you're predicting their days of survival or something. Regression, the difference is the type of variables you're dealing with. Regressions, your input is continuous, your output is also continuous. For classification, your input can be continuous or categorical, and your output is categorical. So the caveat is that all this has to be numeric, right? Your outcome can't be, for instance, how the what the first word the patient says when they wakes up. That's not really quantitative, and machine learning, you really have to deal with quantitative data. So this is an example of linear and logistic regression. On the left is linear regression. You can see the machine learning model is trying to adjust this line so it best models the data. On the right is logistic regression. So this is useful when you have two classes. You see the logistics curve is like this S shape. So it really splits the data into this group at the top and this group at the bottom. So logistic regression, you can see, can be used for predictive binary classification. So logistic regression is not good when the outcome classes are, they're kind of convoluted. They're not linearly separable. Like there's no clear split using the variables to separate into two subgroups. In these cases, you have to use more complex methods. So one of these complex methods is called a decision tree. You can use this for classification or regression. It's most commonly used for classification, and your data can be a bit more complex, right? And the benefit is that it's really interpretable. So I'll give you an example of a decision tree that is used in clinical practice, but people don't realize it's called a decision tree. For instance, this is a general clinical approach for dizziness and vertigo. So first you ask the patient for their history, whether the vertigo is episodic or continuous. If it's episodic, you go through one branch. If it's continuous, you go through another branch. And then you ask other questions like, is it triggered or spontaneous? And depending on which branch you are, you ask different questions and you progress through this tree. At the end of this tree, when you finish asking your questions, you end up with some sort of diagnosis or some sort of decision, right? This is a clinical flow chart. It's highly interpretable. This is what a decision tree is. Now, in machine learning, we try to quantify that, and we do some math in order to optimize it. So the example we're going to use is, let's say we have data for 10 days of weather. The weather is either sunny, cloudy, or rainy. Temperature, humidity, wind are the other variables. And we want to predict if there will be an attack by Sauron or some evil villain, right? So this is remember our definitions. So the weather, temperature, humidity, and wind are our input features, and the attack is the outcome that we want to predict, or the target that we want to predict. So what a decision tree will do is it will take these features and it'll create the flow chart, and it'll use math to adjust the thresholds and also decide where to place, what variables to include and where to place them in order to have the highest prediction accuracy. So for instance, this is one example of a decision tree that can be made. First, you look at the weather to see if it's sunny, cloudy, or rainy. If it's cloudy, you know that Saurons get attacked. If it's sunny, then you have to look at humidity, see if it's high or normal. Depending on that, there'll be attack or not. Or if it's rainy, then you look at wind. So how do you know which variable goes where? How do you know you look at weather, humidity, and wind first? Well, then this is part of the machine learning process. You initialize some random decision tree, and then you run through your data and see how it performs, and you update it afterwards. So for instance, this is your input features. And then, for instance, you'll create thresholds. You update and optimize feature thresholds. For instance, humidity, you'll say if it's above 75%, there won't be attack. If it's below 75%, then yes, there will be an attack. So this is a very general overview of how decision trees work. There's a more complex algorithm called random forest, where you generate hundreds of these decision trees and then you sort of average it out. It's to take care of your outliers so that you don't just get lucky on your first tree that you made. But this is an example of that's fully machine learning. It's implemented in practice. I think there are at least 10 clinical guidelines that use this method to analyze their data. And if you have your own statistical data, if you're doing a research study, this is something you can consider implementing, right? When you have all your variables, you want to predict some outcome, some risk, or some event, you can use machine learning to implement a decision tree, create a nice clinical flowchart with higher accuracy than logistic regression, and it's completely interpretable by clinicians, so they'll love it in publications. And we'll have some code for this that you can feel free to take and you can copy and use for your own purposes. The caveat for decision trees is that you can do something called overfitting. So for instance, the model on the left, this separates these variables into these two classes, and you can tell it has 100% accuracy. So this is great performance. But you can also get 100% accuracy if you make a really convoluted, deep decision tree where you look at every single variable, and every patient with some combination of variables will get predicted correctly. This is called overfitting. When your model is too complex, you can predict any patient in your training set because you have all the variables to take care of their specific characteristics. But when you perform testing on new data, your model will fail because you're unable to generalize and adapt that new data. So on the figure on the right, you see that this complex decision tree has, as you grow the depth, you have better and better training accuracy, but your testing accuracy starts to decrease, right? So there's some balance between the complexity, the depth of your decision tree, and how generalizable it is and where the best model is. So from first glance, it looks like around a depth of 20, you get good balance between test and training accuracy. But there are ways to optimize this. So the other model that people always mention is neural networks. So neural networks is, it's not interpretable at all, but it's very, very complex. Right? You take a variable, you do a lot of intermediate math, and the output of those calculations feed into other functions in between. Next week, we'll talk a bit more about this, but I actually did receive some questions about this. So I'll go over this really quickly just to show how difficult it is to interpret. Let me annotate. So let's say we're trying to predict whether the patient, like their hair color, right? Say this is blue and this is red, right? Our inputs is, I'm picking really arbitrary variables, height, age, right? And I don't know, nail color. These are really arbitrary variables. So what a neural network would do is, first, it takes this value. Let's say your height is 150 centimeters. It'll multiply by a weight. So our weight, the weight initializes some random variable. So weight, it takes 150 multiplied by some weight, 0.5, and then it feeds that output to this hidden layer. So this in each hidden layer is something called an activation function. Usually it's a sigmoidal activation function, which is 1/1 minus e to the negative x, right? So it takes this output and then uses this as this x value, right? And then the output of this, which is some number, let's say it's 0.75. Now it travels along the next branch, and this has some other weight. So let's say this weight is 0.7, right? And then finally, this value is one component that gets added to whether we predict their hair color is blue or not. Now, it gets complex because this node also gets contribution from the age and the nail color multiplied by some other weight. So there's another weight here, there's another weight here, right? So every single node in between is going to be some combination of weighted values of the previous nodes. And then you have this other node, node 3, node 4, and these all contribute to whether you predict it's blue or not. And in the first pass, it's going to be low accuracy, but then the neural network will go backwards and update all the weights in order to, it's sort of selecting which nodes are relevant in order to optimize the prediction by weighing certain nodes, increasing the weights of certain nodes and decreasing weights of another nodes. This is, even in first glance, and this is the most basic neural network, this is highly uninterpretable, right? I mean, you can go through the math and see how the numbers work, but no one's going to see that, oh yeah, height multiplied by 0.5 plus age multiplied by 0.7 into the 1/1 minus e to the negative x function is a good predicting variable, right? That's not really interpretable. But these neural networks have high accuracy for complex problems, which we'll see next week when we look at medical images. So in most cases, I don't recommend using a neural network. Okay, every time I annotate it, the share screen slides don't work. So let me try again. Okay, I got this. I got this. So there's this nice diagram by sklearn, which is the Python library for common machine learning models. It's a decision tree by itself to pick a machine learning model. There are other really popular ones like k-nearest neighbors, which was actually invented in 1951. So this stuff is kind of old. Support vector machines, which you look at your data in higher dimensions and you try and create a curve, like a 5-dimensional curve to split your data. And random forest, which is a more modern version of decision tree. So the one when medical students ask engineers for classification models, the one that I always recommend is look at random forest because it's really interpretable. It's also high accuracy. But you should also do your due diligence and implement other models to make sure you're not just getting lucky with one specific architecture. So I know that's a kind of technical and complex. So if there are any questions, feel free to ask at any time or type in the chat. We're monitoring the chat and we can answer at any time. Also at the very end, I'll stop the recording and then people can ask questions then too. Okay. 1 minute question break while I get some water. So a lot of these Lord of the Rings memes actually came from Prash, who was a huge Lord of the Rings fan. So he's the one of our PhD students at UBC that develop a lot of this content with us. Yeah. Okay. Usually there are no questions during sessions, so I'll keep going. But feel free to ask at any point. So, okay, let's say we picked a model. Okay, now what? Well, remember our best practices. First thing we want to do is explore the data. You can do some visualizations and plot it. In clinical journals, you usually have to do a demographic table 1 that shows your standard deviation and mean of every single variable. That'll give you a sense of outliers and which variables are usable. When I mean usable, I mean they have good quantitative information. For instance, if we're predicting heart disease and one of your variables is how the patient reports they feel in the morning. And let's say it's a scale from 0 to 10, where 0 is not good and 10 is really, really good. Well, that's a really subjective variable. If you don't have anything else, then yeah, you can use it. But through the exploratory data analysis phase, you can screen out what variables are nice and quantitative and what are more abstract and difficult to grasp. It's still usable, but it will be difficult. Next step is to prepare the data. Make sure you remove any outliers, any missing values. You have to decide whether you want to completely censor the patient or to fill it in, let's say, using the average of all the values, which is sometimes done. So it's usually, if you have enough samples, you just censor the patient and remove that patient because they don't have enough data. And then also define your outcome, what you want to predict. So now next is how you split your data. You need to split. So this is this part. If you just do this, where you split into training, validation, and test sets, this is called holdout testing, where you have your data that you use for training and you're blinding it until testing. So some people ask, like, what's the purpose of this? So there's a good analogy to studying, actually. So imagine you're studying for exam. Okay, training is when you're reading materials, reading textbooks, lecture slides, your notes, where you're really trying to prepare yourself without knowing what the test is. Validation is something that you do before tests to see how you perform in data similar to the test. So validation will be like doing practice tests. And then final testing will be taking the actual final exam. So ideally, you're not exposed to that final exam until the very end, but you can do revision and validation in order to improve your model as best you can before the final testing stage. Another important concept is you want to balance your data. Right? You want to, it's like, for instance, when you're studying, you want to balance the type of questions you want to study. If your exam is on everything, you don't only want to study respirology, you want to also study cardiology, OB-GYN, and family medicine, right? So here's our data set. And let's say they have 3 different distributions. You want to balance your training, validation, testing sets so that they all have the same distributions, so that you're not over-prepared for one specific subgroup. Yeah, hopefully this is kind of intuitive. So there's some statistical assumptions that you have to make, and this is just part of formalism in case you ever need to declare it. So your data should be independently and identically distributed. If anyone's taking probability, that means your patients or your data cannot appear in more than one set, and they cannot be related to another set. So if you're looking at medical images, you can't use the same images from the same patients in your training and testing set. Identically distributed means that a across all the set, each feature should ideally be distributed the same way. It's not always possible, but you should do it the best you can. And in the actual training process, well, first we train the machine learning algorithm with the training set. We validate on the validation set. And then the one strategy, like we mentioned before, is cross-validation, where you create, you shuffle around which set is the validation set, and then you average the validation accuracies. And the next step is you sort of update the model. The model will update itself based off the model algorithm, but there are always human input parameters that you need to adjust for the model. So once you have good validation performance, then you can check it on the test set, right? So cross-validation is also very, very important. Another option people do is that instead of holdout testing, where they split from training, validation, and testing, they only have training and testing. And then they cross-validate. So they use their test set 5 different times, and then they average the cross-validation accuracies. In a lot of papers, that's actually preferred. In a lot of papers, the holdout testing is when you have something really foreign and really external that you test on this external data set. But you can do both. So the last slide mentioned hyperparameters. So parameters versus hyperparameters. Parameters are the variables intrinsic to your model that the model would optimize by itself, like the weights in that neural network model, or the thresholds in the decision tree model. Hyperparameters are usually user-defined parameters that the mathematicians, they don't know how to optimize it. So you have to optimize it by observing the models, such as how deep do you want your decision tree to be? The model doesn't know. There's no solved solution for that. So you have to adjust that until your model is optimal. So the analogy is that parameters are like studying ECG by studying, the waveform of the ECG, right? The waveform will always have these similar parameters. Hyperparameters is how you study it. For instance, are you going to study using flashcards, textbooks, or through YouTube videos? These are ways to define how you learn. Let's see. The question is, if you remove outliers before you train the algorithm, does that mean you have to remove outliers for any use of the algorithm? Yes. If you remove outliers, that means your model can't handle, you're saying upfront, my model, I don't think can handle these outliers. So we want to train, and our task is to predict this outcome without this outlier data set. So in the future, if you identify patients with these outlier variables, then you say, well, my model's they're not in the eligibility criteria for this model, right? So ideally, machine learning algorithms, if they're good enough, you throw all the outliers in. So as much as I can, I throw as many outliers in, because that really helps the generalizability. Then you can say that it can predict for any patient population. But that's a great question. So how we evaluate it? So common metrics are, if you're predicting something, you want to evaluate your accuracy, your prediction accuracy, your sensitivity, and specificity. And then from that, you can build a receiver operating curve and get the area under the curve metric. I think this is in biostatistics training for most undergraduate medical curricula. So I won't go over the details, but these are common metrics that are okay to use, and you should look for these in these papers. The pitfall is, don't just look at accuracy. Some papers will only present accuracy, like that Apple Watch diabetes project. They only presented the accuracy, but not their sensitivity and specificity in the article. In the actual full study, I think they actually did, but in the news article, they did not. So there's also some other ways to assess it, which are not as commonly used. One is sort of a regression. In regression, you look at some regression metrics like your sum squared errors. You look at how close your model is to your actual data. There are metrics such as a mean distance error or sum squares or like Levenberg-Marquardt errors. You don't have to know these in detail. You just know that these do exist. The key takeaway is that your accuracy metrics are dependent on your task. Depending on what you want to do, classification versus regression, you'll have different accuracy metrics. When you're using medical imaging and you're trying to predict if, let's say, you're trying to classify a certain set of pixels, then you need some regional metrics, and something that's suitable will be like a dice coefficient, which looks at sort of the overlap and the offset of your predictions of those pixels. A lot of times these models will be trying to predict clinical outcomes. In these cases, there are metrics such as patient recovery, surgical errors, or ICU incidents. These are more numerical and binary variables. So you can use things such as sensitivity, specificity, and accuracy. So now this is the final slide. So the general guidelines for selecting a model is the big takeaway is the trade-off between complexity and interpretability, right? Of course, you want to pick the model with the best accuracy, but then there comes the question, let's say I have a neural network that performs at 90% accuracy and a logistic regression that performs at 89.9% accuracy. I would always pick the logistic regression model because it's more interpretable. You can tune it much more easier, and it's less sensitive to overfitting. Now, with all your studies, you also have to perform statistical tests, especially if you're comparing to some existing standard. If you're using your machine learning model to predict something, and then there's some existing guideline, you want to compare the prediction accuracies to those existing guidelines, and then do your statistical significance test to say that, hey, my machine learning model is actually doing better. So, and then there's some general considerations, like I said, complexity, interpretability, training time. The more complex it is, usually it costs more to train and you require more data. So, and this is a diagram where you're looking at the trade-off between accuracy and precision. So some clinical use cases, you want more precision than accuracy, but this is completely task dependent. This is the actual last slide. So this is a great diagram showing the trade-off between accuracy and interpretability. It's not 100% the case that a neural network is more accurate than random forest, but most of the time it is. And in every project I've been with, this has held true. So at the very bottom, our classification rules say, like, if the patient is presenting with headache, diaphoresis, and hypertension, immediately diagnose pheochromocytoma or something. That's a classification rule, right? And then you move to the left, it becomes more accurate, but less interpretable. So at the very top are neural networks, which are very convoluted, difficult to interpret. Next would be something like a random forest, which is much more interpretable, but sometimes less accurate. And then you have support vector machines, graphical models, k-nearest neighbors. And you see that the example went through decision trees. It's actually somewhere in the middle. So it's about middle tier accuracy, but also very, very interpretable. So this diagram is, if you just search accuracy compared to interpretability of machine learning models, you can generate this diagram. We'll also give this to you in the lecture slides posted on the website. But this is something I always reference in when I'm doing new projects to try and see what model I should use as a first stab. If I'm doing something with a clinician, usually I want something really interpretable. If I'm doing something purely to prove that it can work from an engineering point of view, then I usually go with something super, super complex. So we'll take a 2-minute break. So that's all the slides that we have. And then we have our programming example, which I'll paste in the chat. At this point, are there any questions? I know it's some of the materials a bit convoluting and dense, so I'm happy to answer any questions. Share. Okay. So I pasted.
Sorry, question.
Yeah.
How much data would you need to kind of from a publishing standpoint, be like, this is enough to make sense that what I'm finding is actually is more likely to be real than not?
Great question. So I'll the lazy answer is, yeah, there's no upper limit as much as you can, but I'll give you some use cases of what's gotten accepted in the past. So when you're doing something as a proof of concept that's really complex, like doing medical images, usually 200 images gets you accepted in middle tier journals. If you want to go for Nature, Lancet, they usually want over 1,000. When you're looking at point data, like variables like you have age, hypertension, diabetes, past medical history, and you're trying to predict another point data variable like heart failure or something, then you want usually around the 400 to 500 patient mark will get you published in a clinical journal. If you want to go for lower sample sizes, usually you have to sell it with some engineering ingenuity. Like this is like unusable data set that no one has ever had a signal before. But with our method, we're able to get 0.75 accuracy from 100 samples. Like if you want lower samples, you usually have to pair with engineering ingenuity. Otherwise, I recommend usually 400 to 500 is a good number. Of course, 1,000, 2,000 makes data scientists a lot happier. Yeah, hope that answers the question.
Yeah, it does. Yeah, thanks.
Okay. So in this example, we're going to actually implement a machine learning model. We're going to implement a decision tree. So this is all available open source. So if you have a project that needs some sort of predictive analysis, feel free to take the code and use it for that project. Acknowledgement would be nice. The only thing you can't do is say that you invented all the code by yourself. So that's our only caveat with using this code. So first thing we're going to do is import our data set and a bunch of helper libraries, because about 99% of programming that we do is copying other people's work. So we're going to import some existing code to make our lives easier. Okay. And these last lines, the matplotlib inline, the plot.style, these are just defining how we want our plots to look to make them look nice. Okay. So our problem is we're going to use the same breast cancer data set. So for, I think, 530 patients, we want to predict if their tumors are malignant or benign based off their imaging features, such as the perimeter, the texture, whether there's, I think, inhomogeneities in the textures. So we're going to load our data set. So this is an existing data set available in these libraries. Generally, in most projects, you're going to load it from a CSV file or Excel file. So the command for that would be load pd.load underscore CSV. But this is an existing data set, so we're going to load it with this specific command, load breast cancer. So again, to run it, you either press the play button or hold shift and press enter. Okay. So if there's no error and there's a check mark, that means your code has run successfully. So it loaded this data set. So, and we did this last time, so you can reference the previous notebook to see what the data set looks like when you load it and do the exploratory data analysis. So we want to create a decision tree. All right. So the first thing we have to do is split our data set into training and testing sets. There's a way to do this using the sklearn library called train test split, and it asks you to pick your data set, pick your outcome. So and then select the random state, which is how you randomly initialize it. So we just picked 13 arbitrarily. You can choose any other random state, and you'll get slightly different accuracies. Okay. So now we need to store the training and validation accuracy results. We create these empty arrays to store the results in the future. And then what we want to do, remember I said there's a hyperparameter with decision tree, which is the maximum depth. There are actually 3 other hyperparameters, such as the minimum samples in a node before you terminate it and everything. But we're just going to look at maximum depth for now. In a full study, you want to look at, I think, usually 3 to 4 hyperparameters, and you want to sweep through them to make sure they're optimized. We'll just show you an example of one. So we're going to look at maximum depth. We want to test a range of depth 1 to 16. The way we do this is we're going to run a loop. We're going to build this decision tree every single time, fit it on our training data, get our training accuracy, and also get our validation accuracy, and then see how that changes every time we adjust the depth. Once we get all our accuracy metrics, we're going to plot our training accuracy and validation accuracy and see how that changes. So I'm going to run this section of the code. Right. So we see that when we increase the depth, as expected, our training accuracy increases to 100%. So there's actually a funny story. So one of these machine learning challenges, one of the companies, they presented with 100% testing accuracies, and it turns out they somehow got a hold of the testing set and they trained on testing set and completely cheated. So every time you see 100% training accuracy, your eyes, you start being suspicious. So for the testing accuracy, we see that it sort of peaks at max depth of 3 and then it levels out, right? So it's not that bad. It doesn't completely go down to 0.70. So at some point, even though we are overfitting, the tree is not creating too many sub rules for subgroups. The question is that what is the maximum depth? So it looks like it's 3. So let's set the maximum depth to 3. And we're going to essentially rerun the exact same code. We're going to build a decision tree, get our accuracy, but this time we're going to visualize our decision tree. So there's a specific library called SVG, which helps us visualize objects in Python. So we're going to leverage that to see what decision tree looks like, right? Every time I run this, the medical students, they get really excited because it's something really tangible. So our training accuracy is 97%, validation accuracy is 93%. Right? This is already published in literature like 10 years ago, so this is nothing that amazing. So this is what the decision tree looks like. You can tell it's real interpretable, right? The first variable you look at is the worst radius of the image. If it's below this threshold of 0.109, then you move to the left bin. Otherwise, you look at the right bin. Next, you look at concavity, worst concave points. And then after that depth 3, then you go and classify. So if your worst concave points is under 0.309, then you're going to be benign. Well, you're going to be benign regardless. But if your worst concave points is above 0.87, then your class is malignant. So you can tell this is really, really interpretable. It's like a clinical flowchart, right? So physicians love this. You can tell why physicians love this method. The downside is that it feels a little bit obscure. Like, wow, you're selecting 0.109 as your threshold. Imagine selecting a blood pressure threshold of 123.85 systolic. It's a little bit obscure. So a lot of these clinical rules, they like using whole numbers. It's not the most accurate mathematically, but that's some trade-off you have to discuss if you, for instance, run a clinical trial in the future. Okay, now we can also plot our results as a confusion matrix, which shows the sensitivity and true positives, true negatives, false positives, false negatives. So our confusion matrix looks like this. So we can see that our true positives, we do pretty well. And we're predicting negatives, we also do pretty well. Right? Usually you want to present this in a paper. Not necessarily the exact confusion matrix all the time, so you're running low on figures, but you want to present your sensitivity and specificity. Now, we can also cross-validate, which is what I think every single machine learning project should do. So again, we're saving one subset of the data for testing, and we're shuffling which subset of the data is testing so that everyone gets a chance of being in the test set, and everyone gets a chance of being in the train set. And then we average the accuracies. So you can tell it's like running 5 trials. You'll get higher statistical power to validate your model. So then if someone just has a really lucky model, they won't get away with it. Okay, so to do this, there is a function in sklearn that luckily helps us perform cross-validation called cross-validate, and you just tell them how many k-folds you want to cross-validate. So we're going to perform cross-validation with, again, sweeping through the depths to see how the cross-validation accuracies change. And because we're doing 5 trials instead of just 1, we can get averages and we can get standard deviations. So which means we can get confidence intervals, which gives us much better statistical clarity of the performance of our model. So we're doing pretty much exactly the same thing. The only thing different we're doing this time is we're cross-validating the results before we get the training and testing accuracy. So we'll run this section of the code. And then this is the exact same plot, but this time we get a range of our accuracies. So when we're cross-validating, let's say we're still selecting depth 3. Our testing accuracies that we want to report, our 95% confidence interval would be then from 0.93 to let's say 0.89, right? This is a really nice figure to have in paper, your cross-validation accuracies for your model, because this tells any reviewer or anyone looking at it, this is how our model performs when we try to use different testing subsets. So it's likely more generalizable than if you just present one number. If you just present, hey, our training accuracy was up here. If in the paper, this is all you present, our testing accuracy is 0.93. People are going to say, well, did you really validate it multiple times? You don't really have statistical power in that metric. But when you have something like this, then this tells a story of, hey, even when we try different data sets, we still get some better accuracy. Now, there is a caveat though, right? All this data is trained from data from one center. So you can't get FDA approval for this yet. You still have to do external validation with multiple centers, multiple patient populations, and diverse patient populations in order to capture some outliers that are appropriately captured, like different imaging machines at different centers, for instance. But anyway, this is a general overview of how the machine learning pipeline works and how we generate meaningful metrics that are useful for interpretation. Okay. So that's all I have. So at this point, are there any questions with anything? I'll stop the recording first.